try that. It looks faded though, I don't know why. Okay, well I'm going to talk, and I'm not doing anything on, there's no fracture propagation test or spatial, well a little bit I could touch spatial variability I suppose. But you can go on from there. And this is, I'm just talking about, everything I'm talking about is going to be regarding metamorphism. I think this might be something I stole from Mark from eons ago. Mark worked on some of the work with me for a few years ago. And so I'm just going to talk about everything I'm going to talk about as far as metamorphism. All has to do with the energy balance, basically at the surface and what's coming out from the ground. So you can click that. And these aren't, I don't know why it's so dark. But anyway, basically what we're looking at is the exchange from the snow surface, which is hard to see, with these various trees. So this is just a thermal image. That black up there is just a hole in the clouds. So showing there's a lot of exchange between a surface and everything else around it. So we've done some modeling of that kind of thing. And when I click on it, and this is some thermal modeling, and this is on at the Yellowstone Club. And what we're doing, you can see the sun rising. It's south here, and the sun is moving up across here during the day. You can see the shadows starting to move across, and this is all modeled using something we've been working with for a few years, and we continue to try to improve. But this is where I could talk a little bit about spatial variability, because it varies not only spatially, but it varies temporally too. During the day, it's going to vary quite a bit. So any undulations in it, it's going to change the exchange between surfaces. And what we're modeling here is all of the radiation that's coming in, all of the radiation that's going out, the heat transfer that's coming out. We give properties to the snow. We give properties to the trees. We give properties to the rock. We give thickness to the snow. So we put all that in. We use some LiDAR data, digital elevation maps, in order to derive these things. And so basically, that's what we're doing here. So these are broken up into little pixels, and we're measuring these. So you can see the trees are going to heat up early. The shadows come across here. All these things are exchanging with each other. So that's kind of where we're going. And then start to look at what happens to the metamorphism. I'll talk a little bit about temperature gradient and get a little bit esoteric on that, but you can ignore me if you like. Basically, depth torque, we've got thermal energy moves from the insulated ground up towards the cold surface, so heat flow. Heat always goes from high energy to low energy, always goes from hot to cold, so it's got direction, right? Always has to have direction. It's not just a good idea, it's the law. Okay? So we have, but doing that in the lab, so we do a lot of our work is at the Yellowstone Club, and these folks have done an awful lot for us, so we couldn't do any of this stuff without them, or a lot of this. Well, there's stuff in the lab we could, we have nothing to work with though. So what we do, we go into the lab, and we've built these SubZero Labs that Doug mentioned. There's like 8 labs, okay, different cold chambers for various things. So we make our own snow, and you know, sort of make little computer snow and put it in there and grow it. And so we get reproducible samples. And in this particular room here, designed so that the ceiling temperature I can control independently from the room temperature. We can put a metal halide lamp, which does a reasonably good job of simulating solar radiation, room temperature, air humidity, and that sort of thing. So from that, and this is actually on this video, is some temperature gradient measurement does on a microscope where we have a cold stage. And you can take a look at this, and it's warm up top and cold on the bottom, so you think about your temperature gradient. And we've got this grain here is giving up its mass, moving across, and depositing on that surface above, which in a natural snowpack, that would be flipped over, right? So we're looking at this kind of thing. How does mass move within the snow to cause this reconstruction? And we know it does a pretty good job of that. So on this video, that's not too much to talk about here. Take a look in. We got this one. We're losing it to this one, and that's going to happen. The other thing that's happening is mass doesn't only move in the vertical direction. It'll move to the direction of the lower temperature gradient. So it'll move from here to here. So it's not totally vertical movement. It's going with the largest, not macro scale gradient, but the smaller gradient, which would be 2 grains that might be offset from the vertical a little bit, okay? And what happens is we get these chains, which all you guys have looked at, And I started questioning, well, why did these develop? Is there anything we could say that's a little more than just, yeah, the way they develop? You know? And started thinking about entropy, okay? The entropy of the universe is always increasing. You know, I like saying that, you know, it does. And so what it's trying to do, it's trying to equilibrate things. Entropy tells us that everything is trying to get brought into equilibrium, okay? So everything's trying to get to a nice happy place where everything is trying to get rid of gradients. So it will move. Nature will move. So I tend to anthropomorphize snow. I've spent too much time digging in it, I suppose. But it's trying to optimize something. So if it's cold here and it's warm down here, it's going to try to find a configuration that will bring those together. Can it do that? You know, rivers tend to want to optimize. It wants to take things that are way up here with a high potential energy, bring them down to the valley. It's trying to equilibrate everything. So energy's trying to move things. So these grains set up, and this is one I'll run through a couple of times. It's a little dark, but what happens here, you can see the grains grow, and this one's warm here, cold here, but you can see these things developing. So I'll run that one more time since you kind of know what you're looking for now. And watch, and mass is moving transverse and up and down. It's not just in the vertical, it's dominated. It's that temperature gradient that's causing it all to want to go this way. But a grain over here might have a shorter distance, maybe a smaller temperature difference, but also a much less distance that has to travel. So it'll shoot a little particle of mass over there, little particle of mass over here, and it will come, I believe, into some fairly uniform structure where it'll be, these columns, in my opinion, should eventually, given a certain set of conditions, should have a certain spacing, certain size, certain spacing. May not change the density. You know, I can have a bunch of, and I thought about this when I was looking at some Antarctic ice, and we were freezing, things were freezing from the bottom and getting all these strange little tubes that were growing, and kind of came to the conclusion about how gas was moving to form these ice things. And I said, why wouldn't this do the same? So I started thinking about that. And these things are definitely forming. And now the second law of thermodynamics, it doesn't matter too much, and don't worry too much about it. But basically it says things go from hot to cold, things go from high energy to low energy. Mass flows from a high concentration to a low concentration. And right now they kind of, the way we're modeling it, they kind of work together. But we should be able to separate those and see which driving which. We won't get into that. And when we talk about this, we tend to talk about isolated systems, so we draw a little what we call a control volume. And then have things coming in and going out, we control the boundaries and those kind of things. And it's spatially uniform properties, it's trying to get rid of gradients, which is really important. And to me, this when I started working with this a little bit more, became more interesting than just this. Everything is trying to find equilibrium. So now I find myself looking around going, well, that wants to go here, because that's high there. But what we have to decide is, and we can model these things, but we have to know what we're trying to model. What is it trying to do? So the assumption we made here is that it's trying to get the heat to be in balance. It's trying to get the ground and the air to be the same temperature, however it can do that. That's the assumption. Could be right, could be wrong. But that's what our assumption is here as we go through this. And it's going to maximize entropy. And the production of entropy, a little bit different than entropy, so it's building. Something's happening over time, and it's trying to get to its happy place. And so we thought about a couple of things. When snow basically insulates the ground, and it sits at about 0 degrees. Some of the slopes up the club are very, very porous. They might be -40 because there's all this scree slope and stuff. But they tend to be fairly uniform. So is it a temperature gradient? I mean, is it a fixed temperature at the bottom? Or is there a certain amount of energy that's just getting passed through there, so we have a constant energy flux, or thermal flux, coming to the bottom of that snow? And who cares? And maybe we don't, but I did, okay? So should we control what happens to that bottom? Is it a bottom temperature that we want to hold fixed, or is it a bottom bottom flux? So the difference being the fluxes hold that flux, the amount of heat that's coming through a surface area per unit time, or we just want to hold that temperature constant. And what happens? So we did that, and when we did this in the lab, we ended up in both cases, we did get these chains forming. couple of things happen. As I form these chains, it's going, so you think about ice is the best conductor of the system, right? Air is not a very good conductor relative to the ice. So if I could take the same amount of ice and I could arrange it all in columns, it's going to want to transfer that energy along those tubes, or along, not the tubes, but the ice columns itself, more efficiently. And what we did measure is the thermal conductivity increases in the vertical direction and decreases in the transverse direction because we got this series of columns. It also makes me think, we haven't measured it, we don't know yet, but that as these things do develop, we get to the point where not just we're transferring that by conduction through the ice, as we open up these pores bigger, now we have potential for actual vapor flow. So we get a buoyant effect where you know, we have a warmer air that's going to take this vapor and start to want to move it through cells. You know, just like you do when you heat up water, you're going to get these convective cells. Is that possible that these things are starting to open up like that, when we start to get this thing? That's conjecture, I don't know. But it seems plausible that something like that could be happening. At any rate, heat's going to move more effectively, we're assuming. And just say, is this moving in the direction we're thinking about? So what we did is we set this up where we had just a box of snow, put some thermocouples in, we can control the room temperature, and then we can control either the flux, we just put a heat flux plate in, so we get a constant watts per meter squared kind of thing moving through there, or we control the temperature. And it turned out that, so what I'm saying is, this is going to facilitate, by conduction alone, heat much better than something moving through here. So the fact that these grains are rearranging, not just in the vertical direction like that first video I showed, but also showing this transverse so that these things can actually construct, because snow is trying to equilibrate the air temperature and the ground temperature. Now this, it's a little dark, I'm not sure why, but this is a thermal image, and the values of these are probably not, I wish that showed up a little better because it's kind of a cool picture. And, but the air would be these blue and this green. They might change temperature here to here with ice and air, but you can't see it very well. But this is more to demonstrate, yeah, these things are lining up, and there's sort of a pattern you can see. There's spacing's fairly regular, so we are seeing the difference between the ice and the pore space between it. So these things are setting up. So the conclusions on that, basically, it's going to try to equilibrate, and I'm trying to talk fast because I do. And so what happened is, if we held the flux constant, then the temperature gradient decreased. Okay, we held the flux constant. Now the snow is going, okay, what can I do? What's left for me in order to make the top and the bottom closer to the same? You know, we're not letting it go there, because we keep throwing energy in. Now, if we took this box, this control volume, and didn't let any energy in, didn't let any entropy in or out, then this thing would all try to find its happy place there and kind of start to equilibrate and get around and whatever would happen. But we're driving something into it, and something's coming out of the top. So what we're doing here, when we made the flux constant, the temperature gradient, we let it come down, and the temperature gradient would tend to decrease. When we made the temperature gradient constant, so held the bottom temperature at the same temperature, constant at like -1, then what happened is the heat flux increased. So in both cases, we ended up with these columns, fairly similar, and they got to the same place, but by different mechanisms. So whether that makes any difference to anyone or not, I don't know, but it's kind of interesting, you know, that we control boundary conditions and get to the same place. Which is the correct boundary condition to use for modeling? I don't know. Maybe they both work equally well. But one will start to reduce the temperature gradient. The other one will change the flux. Okay, we're moving on. Looking at depth Thor, and this will sort of hopefully play into the next section, but we did some experiments a few years ago, and I happen to have some very large ice crystals that I brought back from Antarctica and just sitting in the cold room, and decided, well, what happens if we take them, and this is the crystal orientation. You know, ice is made up of, it's a hexagonal crystal with a C-axis orientation, and then a transverse, it's got an A-axis orientation. So it's a crystal that looks like this. It's different properties this way and this way. So I took a piece and glued it up here to a little piece of plexiglass, and then filled this with snow and gave this a little gap, and just ran a temperature gradient across here So that now we have mass flux across here and depositing on here and on here. And what happens, which we figured should happen, because atmospheric science, this happens all the time, is when we went to where there's a C-axis, it's that hexagonal plate, we got these crystals growing. When we turned it to the side, and it was growing on that prism face, we got these square ones. So depth hoar doesn't have to be these perfect hexagonal crystals we sometimes think about. Neither does surface hoar, okay? It's going to depend on these. So the structure of this is a function of the parent grain that it's depositing on. So I'm throwing a bunch of vapor on, it glues to it, and it starts growing. And the reason we get these are called hopper crystals is we're forcing it to grow in a direction. So it's growing down on this C direction, but it's also got this one, so it's growing like this. We get these stepped things that form these different types. So just some coupons, and we could do that. And then here's a few kind of hopefully nice pictures at least. Just looking at surface hoar. Process here, everyone's pretty familiar with. We got mass loss here, mostly due to long wave radiation exiting into the cold sky. Then we get supersaturated surface relative to the atmosphere. So this is not necessarily at saturation, it's just relative to this surface, it's saturated, so we start to get deposition. I think everyone here is pretty used to that. So we built this. Okay, it looks like a bunch of Boy Scouts, but what we did here, took this, we have water in here, and we're pumping it very, very slowly, but just sort of bleeding it in there at maybe a meter or so per second, a millimeter per second coming across the top. And the ceiling we have at -50, the room is probably -10, and so we have this moist air available across the top of that surface. Now this has been done before, so first thing we tried is make real cold snow in one chamber, and then run it into a moist room and just drop it in there and you get surface hoar. In fact, the ceiling's covered with surface hoar because that's the coldest spot and that's where it's trying to go. It's trying to equilibrate everything. It's all about entropy again. It's taking this mass, ceiling's cold, I'm going there. So we've got to supply it pretty close because given its druthers, it's going to go up there rather than down to that surface. But we can bring that surface temperature down, do that long wave radiation exchange with the ceiling. So we're sucking that energy out, giving it a little bit of moisture, and we grow surface. So these are some, Brad Stanton took these, and so that's a little cup. So what he did is sat the cup inside that, sort of in that chamber with the snow surface that was just sitting there, pull it out, threw it into a CT scanner, and this CAT scan, then we take our sample, we put it back in that little marker there so we could mark it and line these up again. Very patient to do this. But, and then we started looking at the other thing that happens with these crystals, in addition to growing onto a particular surface, so this would tend to, if it's being supplied this way, would tend to grow out from it, pick up that crystal orientation, because it's forming basically the same crystal. But snow, in the atmosphere at least, forms relative to temperature. We'll decide whether it's columns or plates. And then the stellar part is how supersaturated it is to whether or not we get these dendritic structures taken off. So that's kind of what we did with this, and I'll try to do this pretty quick. So it's a CT scan of some of these, and ISSW in Alaska, I think we showed these before, but this kind of the start of the project, of the sample, and then 6 hours later, I think, 6 hours later, it should start to grow. There we go. So this starts to grow, so we're getting this deposition on here. That's just surface hoar. But at the club, we've been talking a lot about it. We sit around and dig out samples, and they've taken some amazing pictures. I mean, they really are. And this year we've seen some really cool ones we still don't know what to do with. But they're growing off these surfaces. And here's one more. So with a little more time, we start to get these other structures. So we just take it, change temperature, start to get some growth. Now this is kind of interesting. Take a look at some of these. See, now this one apparently landed on top of a crystal that was oriented with its A-axis looking upward. So when it globbed onto that, it tended to take off. And you'll notice that's fairly typical in this. And this is a number of years ago, we put out a paper saying, yeah, we think that surface ore or depth ore ought to pick up a certain structure depending on the temperature at which it forms. Because there's an optimum growth. For instance, in water, when it freezes, it grows primarily or predominantly in the A-axis direction. So all the corners would start to grow quick. And that's one of the reasons that it's quiescent. They'll tend to float and be flat and then connect like this way. You get this S1 ice, it's called, and it flows out very columnar structure of all oriented crystals. But there was a little turbulence in there, it might roll over and such. And the A-axis is dominant, so what happens is if I do roll that over, the A takes off and eventually crowds out all the C's, and we get transverse orientation. But so the same type of thing should happen here. And just one more. Let's see. So a little growth. Well, that's good enough. What happens is these things grow, but you notice that these crystals kind of mimic those ones that we saw on the controlled experiment with the little tiny depth ore things, okay? And when we backed off, so these are up close, obviously, we took the same one, we focused in a little closer on these two, the whole coupon, the whole crystal was covered with these things, and they're all oriented. So we're pretty sure that's what goes on. So another thing, this is kind of this was from the depth ore experiment, but a lot of times in surface ore, you'll see something that's just part of it. Well, there was a crystal over here that's not showing up too well, but it's sucking away moisture from here, and this thing can't grow to its full dimension. So you lose a lot of that symmetry. But my contention is that if there's a primary temperature at which these things are growing, the dominant crystal growth is going to be the ones that are oriented to the most productive way to grow. Okay, so that's what they're going to take up, and they will they'll all start growing, but the faster growing ones are going to tend to close off the other ones. Just like in lake ice, when the A-axis gets tilted down, since it grows fastest, it crowds out all the others. So my contention is that should happen in depth ore, should happen in surface ore, just should happen, you know. And so this is hard to see, but Jody Bones and Brad, they were doing an experiment, and I said, take some of these same coupons, which I've melted the cold room, lost them all. But we had them and did it for the surface ore growth, and put them on the surface. It got basically the same result. Not quite as clean as the perfect little box that we had, but A-axis went A and C-axis went C. So surface ore ought to do the same thing that I think depth ore ought to do. And, okay, so just some more of that. So one more type is radiation recrystallization that Carl did a lot for promoting. And I think we didn't think it was all that common until a few years ago when you guys started going out there and people at the club just go, it's a radiation day, and they go out and they dig it and they can find radiation recrystallization, you know. They feel it, it's intuitive now. Okay? So, but they grow, they're just beautiful little things. So I'll just run through some pictures on that, and I'll try to get us back on time. So these are just some of the types of crystals. We did some modeling on those couple of days in February, and we used a thermal model from the field, and we could model it, and they pretty much match what we think we ought to be growing. And the way the radiation recrystallization grows is different from surface ore. What happens here is these short waves, if you look at ice, and I got a nice clean, it's basically glass, I can see right through it. So the short wave, the visible radiation, penetrates through, so it basically goes to some depth. There's a little bit absorbed, and it's preferentially absorbed in the reds, then it moves down to the blues. That's why if you think snow cave, mostly blue left, everything else has been sucked out. So it's very wavelength dependent, and that's something we're just starting to do in the lab too with the hyperspectral camera. We're going to look at how those particles, how the energy is picked off per wavelength. But anyway, that short wave basically penetrates and causes some subsurface heating, but the surface is a black body. So basically snow is black in these wavelengths. So all that energy is getting sucked out. But a black body, it doesn't penetrate very much. It's all right at the surface. So this gives us gigantic temperature gradients right at the surface. So what we did for these experiments is we put our box in there, we turned our room on, and we turned the lamp on and the ceiling on. So now we're getting this shortwave penetration that's penetrating into the snow. the black body part of it, the long wave, is sucking out to that minus 50-degree ceiling. And we get these massive temperature gradients. And in a few hours, we run these about a day. We don't quite get the gradients we've seen at the club, but we develop these things, and we get these beautiful little crystals. They're very tiny, and they're very, very short. And we just did something more recent that's changing some of my thought on some of these. But here's that's very cool, and I like this because this is a snowflake, a crystal, right? And the crystal habit for these things is picking up, and it's just growing off. So we've seen this a bunch now. These things will grow off of whatever that parent. This is a new snowflake, so it's nice and easy to see. That's why I say these guys are taking great pictures. I say guys and gals together, okay? But they're just beautiful. I mean, if nothing else, they're darn pretty. And these are very, very weak. And I'll show you that in a second. The surface looks kind of, they're kind of laid over in some of the CT images of these. You can just see they're very oddly built. This column structure doesn't exist. They're kind of laid over these columns, but they're not the long temperature gradient type columns. They're laying over, and I'm trying to figure out why that is and what it means, okay? But anyway, they look kind of like that from the surface. And if you look a little closer, which I don't know it's more of a thing, but anyway, they're just these little, there's a black thing, and see? So here's that CT, but I don't have it spinning, so it's not as clear. But you can see these things are growing. Now these, I want to point out that they look like they're growing upward. That's because of the way we've done the images, but we're not really sure yet whether my thought is what they're doing is we're losing mass, and actually the surface is staying is dropping a little bit, and we're losing mass, but I'm not positive. There could be some kind of feedback going on, and these could be going on the surface, so we really are not positive, okay? But anyway, you get these kind of very odd-looking structures that are all layered up like this, and for a while I was trying to explain these as some sort of a truss, that maybe that made them a little stiff, because I'll show you in a minute. What we measured is that this radiation recrystallization is very, very soft and shear. But in compression, it got very, very stiff. And I was trying to figure that out, so I was trying to, if you have an answer, you can try to find explain it somehow. I said maybe it's a truss type thing where these things, but I'm not sure anyway that's what it is. And I'll talk about that in a minute. So what we did here, we looked at this in compression and shear. We can also take it and look at it in between, but basically just looking at those two components. And what we do is we take a column of snow. So we take our box, we turn on our lamp, we keep our ceiling on, and then we just let it go to town, and we do measurements before and after on straight. But we let it go to town, and we develop these layers. And then we take these layers and do a couple of things. We cut them out, we put them in the CT scanner, we break them up and look at them in the microscope, But then what we do is we cut out a sample, isolate it, and then put a shear frame. We say shear frame, but it's really a compressive or shear. And we put that on top of it, and then we first we cut out the layer, and then we'll sift a little bit on top of it. So we start out with a sifted snow, so it's very, very strong. Then we run this radiation process over it, and we recrystallize it. You pretty much see that when that's done. Then we sift some more snow on top of that, just a centimeter or so to give it something to purchase this box on top of. And then we put the box on, which has an open top, and then we sift some more snow in and bury it. So what we're trying to simulate here is a rigid layer on the bottom. Let's say a wind blown, right? We've sifted it, and the snow is pretty reproducible because a lot of it pulling from the lab, sometimes from the field. But then we sift that in, that's strong, it's hard stuff. Then we make this weak layer. Then we sift, so we kind of think of it as a hard layer from wind, then we've got this radiation event, and then we've got hard snow on top of it. It does a few things for us. It kind of sets up a nice scenario. Plus, when we load it, we're not going to see as much definition in these places that are sifted, and we're trying to not isolate, we're trying to not notch it. We're trying to see what happens to this thing. Can we just, if we load it, how does it move? So we do that, and then what we do is we take it and we sort of spray the side of it with this pattern, this sort of random pattern, and we have some dual cameras to take a picture. They do some pattern recognition, and then they can, it's basically an optical strain gauge. Okay, so it tells us how parts are moving relative to other parts. You know, this little piece here, this little piece, they stretch. This thing tells us what's going on in it. And it's about 17 frames a second, so it's not very fast. So we're trying to buy a high-speed camera to see if we can see this a little better. But so think about this. We'll do it in shear. We push across here. We've got a weak layer in here because we've cut down below the weak layer and then have this rigid layer here and then another layer on top. So it's isolated, and then we load it. And we try to load it at a rate. It's like strain. Strain is about 10 to the minus 2 kind of. That means anything. Anyway, fast, relatively fast. I mean, it's not fast, but what we want it to do is not have a viscous effect. If you load something too slowly, snow. And I talked at the at those who were at the patrol meeting. I tried to talk about elastic and visco elastic, and I think I had nominal success. But what happened is snow kind of acts a little bit like a spring and then a little bit like some viscous fluid. So it's a combination of those things. So if you load it quickly enough, you can kind of get purely elastic response, which I think is more relevant for jumping on it or for hitting with explosive. So that energy is going to be loaded at a fairly high rate. If it's loaded too slowly, it starts to creep. We know that knocks lift towers over. That's a slow process. So we want to get away from that. So we can go fast enough to kind of eliminate that. So this should be mostly elastic loading. And it's much simpler to deal with than the viscous part. So we load it. There's the frame. We put this actuator here. Here's a load cell. And we push it this way and see what happens. So there it is. So we look at this. This is two different things. This is pure displacement. How much is every particle moving, right? So the top part is moving almost like a rigid block, right? The blue, it's a little bit skewed to the left because we're loading it from the right and there's some deformation going on there. But this is displacement. Remember what it's doing? It's measuring the difference from here to here, here to here, here to here. And it's doing that across this. So that one's displacement. This one is shear. So it's the amount of strain. Change in, this is shear strain, so it's a change in angle. But think of a change in length over the original length. How much is it stretching? So it gives us a particle displacement relative to another particle at an angle. But that's what that is. So, but what we see is it's markedly weaker. We basically look at this as rigid body above and below, and in that middle layer, it's softening for sure. And what we saw is, now this is the way we've loaded it. And so this is the amount of load we've been putting on. I'll try to scream through some of this. And so this last column over here is going to be this is the change in strength from the original sample. So it dropped by like 84% in strength and shear from before and after. Okay? There's a little bit of noise in here. There's lower density snow. Actually, it went up a little bit. But the others fairly consistently were doing that. And this is showing right here, should have mu up there, I don't know where it went to. But it's saying that basically the stiffness, so not the failure, but the stiffness, how soft is it, also decreased here, 13, 15%. So it's softening for sure. And it's failing. Okay? And then in compression's a little harder to run, but because it's not as clear cut at where it's failing. But basically, it got stiffer by several hundred. It got way stiffer. And like I say, I'm trying to explain this, and it's been a little dicey. And then the change in strength, it got nominally weaker, but not as clear cut. A little weaker up here, a little stronger in compression. So this is a particular type of snow grown in the laboratory from laboratory snow. Okay, that's where we are. But it definitely got weaker in shear. It got softer in shear. It got stiffer in compression. Now what's something we just looked at last week. And I think this just summarizes what I just said. Decrease in shear, increase in vertical, decrease in strength, but a little mixed results there. So that's kind of the results from that. But what we noticed a week or so ago is David was pulling some samples apart. And we've been concentrating on that weak layer. There's all these things that are laid up like this. And what he saw was that below that weak layer, now we're talking less than a millimeter, we have little depthors, little cup-shaped things that are hanging on below there. And that's where I think it's failing. I don't think it's failing in this very, very ornate top layer. I think it's failing in this layer that's just below it. Now, whether that makes any difference to anyone in the field, whether it fails at this little layer or this little layer, it's irrelevant. You know? It definitely is getting weaker because we weren't even parsing that at this point. And we didn't even notice it. And when we guys are grabbing samples at the club, they're always pulled out together. So we just sort of lump them all into one thing. But I think there's two different processes going on. And this is where I say I'm not really sure what's going on with, as far as that top layer. Is there some weird mechanism? They have these frost flowers or something that grow on ice, and that actually the vapor somehow redeposits onto the surface. That I'm not really clear. But some other process going on at that top layer that might be different from this depth horizon layer that's just below. We're talking millimeters here. We're also talking a couple hundred degrees per meter gradient, so really hard gradient. So it's kind of where that is. And okay. Good job.